Hello, it's good to be back with you again. Today I'd like to talk to you about how to solve systems of equations. Now before we get into the mechanics of how to do this using MATLAB, we need to get two things out of the way. The first thing we need to know is what is a system of equations, and the second thing we need to know is why do I care? Well, the first part's pretty easy. Let's write out a system of equations. Well, let me write out two equations and we'll decide if they're a system. If I write out this and this, those are two equations, but they don't depend on each other. The variables in one don't appear on the other one, so I can solve one of them and then solve the next one. So this is a pair of equations, but this isn't really what we mean when we say a system of equations. A system of equations is two or more equations that share variables, so they depend on one another. So I'm going to erase this. Let me write down I'm going to check my screen here so I make sure I get this right. Here's a system of equations that I'm going to use here in a second. Okay, two equations, but these share variables, okay? You can't solve one without the other. Now, what do I mean when I say solve a system of equations? When some propeller head like me assigns you a homework problem of solving this system, what they really mean is find an XY pair, two numbers, one number for X, one number for Y, that makes both of these equations true. That's what we mean when we say solving a system of equations. Well, this one happens to be nonlinear. When you draw this out and plot this out, you don't get straight lines. Let's try something else here. Again, I'm going to check my screen. Whoops, my screen just went out. Okay, there we go. There's two equations. These are linear. Okay, if you plot these out, you get straight lines. Now, linear equations, here they are in 2 dimensions, so you can plot these on a 2D plot, XY plot. In 3 dimensions, you get a plane. In 4 dimensions, I'm not sure what you call that. But the thing they share is that they always have zero curvature. You get a line, a plane, or whatever the multi-dimensional version of a plane is. These are easy to solve. These are very easy to solve. These are hard, and we're going to see why here in a second. Okay, so this is what they are. Why do we care? Well, the reason we care is that physical laws are written out mostly in terms of differential equations. I say mostly to be careful. I can't think of any physical law that's not a differential equation, but maybe there is one, so I'll be careful. Differential equations are very hard to solve in any way but numerically. And when you numerically solve a differential equation, what you almost always get is a system of equations you need to solve. So what's this look like? Well, one that's of particular importance right now is weather models or climate models. The equations that describe movement of fluids like the atmosphere are called the Navier-Stokes equations. They're really hard to solve. In fact, they're almost the gold standard for really, really hard to solve equations. The way everybody solves them approximately is to take a space, a volume, and divide it up into grids and then solve the equations approximately on each of those grids, combining the effects. Well, what does that look like on Earth? Well, depends on which group or which organization is running the models, but there are grids of the Earth's atmosphere. In fact, here's an example. You can see what one looks like. Okay, so with this, what you're doing is solving these Navier-Stokes equations over those grids and adding the effect up. And it depends on the approach that's used. You either wind up solving within the grid or at the corner points or something. But the bottom line is you get a very large system of nonlinear equations that you then have to solve. Well, okay. Another example is a finite element model. Now, these are used for modeling structures almost universally. And finite element models do the same thing. They take some mechanical part and they apply the equations that describe deformations, divide them up into little elements, finite elements, and then solve for all these elements, adding the effect up to find the net effect on the structure. So if you want to look at a finite element model, here's an example. So whenever you're modeling some reasonably complex real physical system, it's very likely that you're going to wind up having to solve systems of equations. So it's very, very relevant. There are many, many practical problems that require this. And if you can't do this, your abilities to work in the physical world or analyzing the physical world are very limited. So let's make sure we can do that. Now, there's a whole field of mathematics called linear algebra, and I'm going to be doing some later talks on how to solve linear systems using the ideas of linear algebra. So to start, let's get this one out of the way. I mentioned in passing that these are hard to solve. Well, what do I mean? Well, how are you going to solve this? Well, analytically, substitution. You know, y equals that. I can put that substitute in wherever I see a y. Well, what would that look like? X squared minus 1 equals y. Well, x squared minus 1 equals y and cosine x equals y. If they both equal y, they must equal each other. And I guess I can do this. Now what? Now what are you going to do? You know, parabolas are easy to deal with, but you add that term on, not easy to deal with anymore. So you're stuck. Analytically, you generally can't solve systems of nonlinear equations. You can do it graphically. I can make a plot. You know, if I plot this out, here's what it looks like. Okay, there's the parabola. There's x and there's y. Well, what's cosine look like? When you zoom in far enough, it looks like that. Now it's going to go off these directions, okay? So right there, let's make sure we know what we're looking at there. That's y equals x squared minus 1, and that's y equals cosine x. So what does it mean to find a pair of numbers, x and y, that make both of those equations, both of these equations true? Well, what that means graphically is where do they cross each other? Right there and right there. If I pick, let me get out of here, I'll get my head out of your way here in a second. If I pick that x, and I'll call that maybe x1 and x2, if I pick that x, y is the same for both of them. That's a solution. If I pick x2, y is the same for both of them. Also a solution. However, to do this, I have to make a plot. Well, how do you do that? Well, you calculate values of these functions a whole bunch of times, and you draw it out. Well, the game we're trying to play here is we're trying to figure out how to solve these equations in as few calculations as possible. And making hundreds and hundreds of points to draw a plot, that's not going to work. Besides, it only works in 2, maybe 3 dimensions. I don't know about you. I live in 3 dimensions. I don't know how to draw anything in 4 dimensions. So the limits of plotting, you can't extend it beyond 3 dimensions. And something like one of those big weather models, I don't know how big those get. Millions of equations, most likely, maybe more than that. Certainly not much less than that. All right, so this is limited. You can't do this graphically either for very many practical problems. Your only real choice is numerical. Now the good news is MATLAB is very good at this, and there's some very powerful, robust solution algorithms in MATLAB. The one we're going to focus on is called FSOLVE, F-S-O-L-V-E. Well, let's go there right now onto MATLAB, and let's take a look at these two equations and see how we can solve them using FSOLVE.